All right, so first off, I have 2 children in the background. I'm sorry, life happens. So you will hear a little bit of background noise from me. No getting around it. But moving on, can you guys see my screen share?
Yes.
Good. All right. This is getting started with microservices and serverless. This stems from a class or tutorial that I've taught several times, and basically we are taking the introductory concepts of microservices and serverless, and the class itself makes it accessible. By the way, are we allowed to plug? Yes, no?
Yes.
Okay. By the way, I give this tutorial at the TechWalk conferences. Agile DevOps Virtual, which would have been DevOps West, is coming up, and I'm giving a hands-on class with all this material. So if you're actually interested in learning it in a hands-on affair, take a look at our conferences where you can have me do it in person in November, or I don't know if I'm up to do it in November, but you can have me do it in person too, if once things clear up. Anyway, moving on, a little bit about me. I'm a 20-year veteran of the software industry, and basically I've been doing DevSecOps for about the past 8 or 9 years. I've been a consultant with Coveros for most of the time that I've been doing DevOps. And I've had several large federal agencies and companies as clients. I've helped build and operationalize automated CI/CD pipelines, automated test frameworks, security frameworks, and helped companies leverage the cloud to meet their business needs, going from all self-hosted to all cloud in both commercial and federal space several times. My experience with microservices largely spans helping customers migrate from traditional monolithic architectures to Kubernetes. And while I'm not a developer, I often have to coach developers as to how to design their application and help them navigate the realities of using containerized Kubernetes environment. So we're going to give a practical approach of how to design and build microservices, use serverless technology, and how the two can fit together effectively. Along the way, we're going to take a look at some of the basic building blocks. We're going to start off with microservices. Now, microservices are an idea. They are not, it's not new, and we'll go into that. So we're going to take a look at what microservices are, what serverless is, how do these things change continuous integration and continuous development, and how they change testing, because they have a significant impact on how we test applications and how we look at them. A lot of people get a failure to launch with things like test-driven development or BDD, TDD or BDD, behavior-driven development, because they're attacking the testing problem at such a large scale. We're going to talk about some of the ways that microservices help you break down the problem so that those concepts become more tractable. So let's start off at the very beginning. What is a microservice? This is one of the better definitions I found floating around on the web, but it's a software development technique, a variant of service-oriented architecture that structures an application, blah, blah, blah. Basically, it takes the idea of loosely coupled services, fine-grained functionality, and lightweight protocols. Basically, you want to be able to have your problem broken down into small code bits that are then orchestrated to provide a solution. And this is just straight off Wikipedia. The reason you want to do this is several-fold, and we'll go into that coming up, but basically small orthogonal units of functionality that are easy to weave together is the overall goal of a microservice. And some people overlook that. They look into breaking down the problem. They think that microservices are containers. They're not. I've seen people, I swear to God, try to stick Oracle databases in a container. Just because it can be containerized doesn't mean it should be containerized, and doesn't mean it's a microservice. So, you know, small bits of functionality that are threaded together. So that's basically what we're thinking of when we talk about microservices. So what are we trying to do here? We want to minimize the dependencies between all the things. You want loosely coupled. So let's talk about loosely coupled for a minute. We want small objects or modules, no duplicate functionality, and complex objects should be composed of many simpler ones. So what this would mean in reality is that you would have, let's say, for example, you could wave a magic wand at your organization and you have Kubernetes running. Some people do, or OpenShift. Some people do. For some people, that would be a pretty hard mountain to climb, but let's pretend you do. What this means is that your application, instead of just being composed of these one or two huge built software artifacts, now might be composed of hundreds or even thousands of small containers working in concert. And they know how to talk to each other, and there are very little dependencies or must-have dependencies between these two containers for each particular container or service to be up and running. Now, you don't need containers to implement microservices. If you were really savvy about it, you could use the systemd functionality of Linux to stand up a whole bunch of Java services that talk to each other appropriately. And you would still be fitting the microservices paradigm. But with the isolation and the facilities and the orchestration tools that things like Docker Compose or Kubernetes offer you, it's just much easier to use these tools to achieve your microservices goal. Next, let's talk about fine-grained. What do we mean by fine-grained? Well, we're talking about the fact that your services should be small in scope. They should do one thing, and they should do it well. And this, by the way, maps very well to Agile and DevOps. You're talking about small bits of functionality that you're composing and you're adding to the application. And this allows you to do things like fit your development cycle into a 1 to 3 week sprint, right? You're only working on one service, which could be in a container. So that is suddenly more tractable than having to make several changes to a huge monolithic container. And this, or monolithic service or monolithic application, and this service might be so old, you might not be aware of all of the dependencies you're touching by making the change. So even though you can make your change in the requisite 1 to 3 weeks, the amount of testing that you then have to do to make sure that you're not running afoul of some unknown dependency that some developer 5 years ago made and has since retired, that becomes less of a concern because now everything is smaller in scope. So in order to do anything significant, you're going to have lots of containers. But the idea is, or services, microservices, but the idea is each service should be able to stand on its own. It might not do much on its own, but it should be able to stand on its own. It should be able to initialize, run, and start taking requests to do something or make some sort of transformation on its own. So, and that thing should be small and understandable. So that's what we mean by fine-grained. Lightweight protocols. When you're talking about lightweight protocols, because, think about it now, you have these maybe hundreds or thousands of small components swimming around, right? As opposed to just having one large application. They need an efficient way to talk to each other. If you have to build, a heavyweight TCP connection or some other protocol connection between all of your containers, you're going to take an enormous performance hit, especially if the task that you want to do has to jump through 6, 7, or 8 different containers, which could now be possible or a possibility. And here I'm using the term container or microservice interchangeably. It's a little bit of a faux pas. It should just be microservice, because like I said, just because you containerize it doesn't mean you should. So the communication between all these containers has to be lightweight and fast. So stuff like UDP, some small TCP. If you can do shared memory, which is definitely possible, you just have to set Kubernetes or Docker upright to handle it. You can do shared memory passing to eliminate a lot of TCP overhead as well. Because like I said, any particular workload is going to be jumping between containers, many containers, and it needs to be able to do so quite rapidly. So what motivates these designs? It's a technical marriage to Agile. We talked about that. You know, you get 1 to 3 week sprints. Microservices allow for meaningful changes to happen in that amount of time because it's only one small discrete unit you're working on. Rolling deployments is another big one. Downtime is becoming less and less acceptable, even for upgrades, even for zero-day security patches. You know, how often does Amazon go down? It happens, but how often? Not a lot. Google has a really good uptime record. They engage in microservice design. But if you have a critical service, if you're able to break it down into small chunks, it's actually easier to keep it up, and it's easier to leverage modern technologies. Kubernetes can use its CO, so that you can have 2 versions of the application running at the same time. And basically what happens is one set of containers is servicing the old version, and another set of containers comes online, start taking old traffic. And as the people are, sessions are expiring, you don't let them log on to the old containers, you just let them log on to the new containers. And then you check your load, and when your load drops down to 0, boom, you've upgraded, and you've done it with 0 downtime. So these rolling deployments are another motivation. And microservices are a way to achieve that goal. Reducing the CI cycle time. If it takes you 45 minutes to build your monolithic application, that means it's going to be over 2 hours before a developer is going to get any sort of feedback by the time it's compiled, unit tested, installed, and deployed to some shared environment, right? 2 hours to see if your formatting text change is correct, right? If you're using a microservice, you just change the particular service you're worrying about. It should sail through the pipeline quickly, go through a set of predefined tests, and be deployed to some experimental environment where you can see what's going on. And you should be able to do that in minutes, not hours. And the faster you can do that, the more frequently you can release to production. And also, it's a reduction of deployment risk. Because you're delivering these small increments of functionality quickly with microservices, you're going to release more often. And this is very important because you're going to make sure that you exercise your release pathways and your release cycles, which is one of the least tested, most fragile part of traditional software and SDLC. If you're only releasing once a year or once a quarter, how often are you going to test the release process? But if you're releasing once a week or multiple times a day, all of a sudden your release process needs to be engineered, automated, and 100 times more reliable, because you don't want that downtime. So what effect do microservices have on application design? Well, new technology has lowered the cost of having many small services, and this looks a certain way. You have containers, functions, and web interfaces. You know, Swagger and a couple of other different technologies now by default expose versioned, simple REST APIs to do things. Several enterprise applications that I've used recently, the UI was just a basically overlay of these REST interfaces. And each one of these REST interfaces, if you follow a good design principle and you make them a microservice, they're their own service, they're self-contained. And basically, you know, that's how you see it influencing modern design. Functions and functional programming is another way, and functions we'll get into, but that's usually, you can see that in microservices, where you can throw a function at the cloud and then all of a sudden it does stuff. And containers gives you that isolation. It's another way. So this is how microservice design has been exhibiting itself in technology. Developers need to also think differently about SCM and how to track changes. So you have maybe hundreds or thousands of these little services composing your application right now. If you're following good practice, you now have hundreds or thousands of Git repositories that are tracking all of these changes. And you have to think about how these repositories are organized. You have to think about one repository for one service, et cetera, which is a departure for some people. Even though in the past I've seen people who try to engage in microservice design, They put all of their services in one Git repository, and then you get all sorts of versioning, branch conflicts, merge conflicts, and it delays the development process. So SCM is a different concern as well. Keeping track of communication pathways is another important thing. You have to take a look to see what it takes to have something accomplished. If you have to jump through 37 services to obtain a single database query result, that's probably bad design. And you need to keep track of what you're doing to achieve your objective and making sure that you're constantly taking the shortest, most efficient path. You have to take into consideration that multiple versions have to coexist for some time. That's how you're going to get your rolling deployments. And lastly, parallelism and horizontal scaling is almost implied at every level. So you have to look for transactionality and race conditions, and you have to look for them up front, because you're going to be maybe activating 3 or 4 different instances of the same microservice. You have to have that as a test case. You have to know how you scale in order to service the load that you're going to be seeing. And we're not talking about Google scale loads. If you're engaging in microservice design and you want high availability, you may just have to have 3 or 4 services to get your high availability. If one of your web servers goes down or one of your nodes goes down, you want it to impact as few people as possible, and having that load spread across these services, the same services, will help you do that. So how does this affect CI? Well, the actual generation of object code should be smaller and faster. There are some exceptions to this. If you're doing a lot of node programming and it's all interpreted, then your packaging should be faster and your creation of deployment artifacts should be faster. But if you're still writing Java, C++, or .NET applications, actually generating a working unit of the application should go from many minutes. I remember one project, the build time was 45 minutes. It should go down to like 2 or 3 minutes. The total build time may increase end to end, because you should also have more automated tests to support fearless refactoring. So this harps on the definition of build. The literal get the code into a package and ready to deploy should, bar none, take less time. You should be running your unit tests or whatever simple quality and static scanning you're doing, and then it should be in an artifact ready to go, be it a container, a jar file, or whatever. But it may spend more time in the pipeline, because in order to support microservices and testing all of the different pathways that data can take through your application now, you're going to have some level of automated testing to subject your new changes to. And so build time shorter, you might spend a little bit longer in time in the pipeline, but your feedback should be faster and you should know what's going on. Your feedback loops should be smaller overall, and you should get higher quality code out to any of your static environments that are going to be shared between people. Failing fast is not optional anymore. You have to fail fast. You absolutely have to get a good idea of whether or not a change is good or bad, because it only gets exponentially more expensive if bad code makes it further down the pipeline when you're doing this because of all the dependencies. In order to help control all of the parallel development that's going on, Git flow or something similar is a must. You have GitHub flow, Git flow, GitLab flow. There are a couple of different variations, but this is a way of managing all of those SCM repositories, possibly using the concept of semantic versioning on top of that to get you where you need to go. Builds must trigger automatically for down or upstream changes. Your CI pipeline should know when something needs to be built if a dependency is perturbed. You shouldn't have to guess, because the dependency tree is going to get huge, and you have to program that knowledge into your CI pipeline so it just does the right thing. Because if you have to figure it out by hand, that's going to be a huge delay between committing your code and getting your code into an environment that works. CI must feed dashboards with results. You need to be looking at the data in the aggregate and be able to drill down when there's a problem. Because if you have to look at the build logs of 37 containers at the same time, your eyes are going to bleed. But if you can look at green, 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 red, you can just click on the red button and see what's going on in that one particular container. And also, you need to look at the parallelization of the build, test, and deploy process. Currently, a lot of people, when they do builds, it's, you know, if you think about parallel programming, it's the critical section of code. Everybody stops and waits for the build to happen. You have to do away with that, and you have to parallelize as much as possible so you can get your small containers through the pipeline as quickly as possible. One example of this at a very low level, when you do your build, you can do your unit tests and your static analysis in parallel. Static analysis doesn't require the application to be built. There's no way, there's no reason, and there's no reason for your unit tests to wait on it. And if any one comes up with a critical error, you just fail fast. Call it a day and chuck that build. So how does this affect packaging? Well, ideally, you're splitting things into two pieces. You have the application code and the application runtime. The code is in a jar, war.o.a, whatever, and then the runtime is a really good idea to manage the runtime with containers. And basically, containers allow you this facility to freeze everything besides the code in a particular state, so you don't have to worry about configuration management. And it does it in a way that two containers won't interfere with each other if they require conflicting dependencies. Say you have two different versions of Ruby you have to run for whatever reason for two different microservices. You no longer have to worry about getting two different versions of Ruby and using RVM on your server just to get things to work. Now you can just throw one version of Ruby in one container, one version of Ruby in another, and they won't know about each other. You don't have to worry about any conflicts. The split allows for inclusion of all system level resources in a neat package independent from the underlying platform. Anything that conforms to the Docker standard, so you can set up your container and it can run on whatever flavor of Linux you want. It can run on Ubuntu, Red Hat, whatever. That container should be portable as long as the standard is implemented. Things get a little bit hairy when you go between Linux and Windows. That gap is closing, but right now things are still a little bit hairy if you want to run on a Windows container runtime. And the runtime in the code should be immutable inside the container with parameters and configurations that can be defined externally. So you want the same container to run in your dev, test, stage, and production environment, and you want to be able to feed in the parameters at start time to determine what environment they're in. But that container should be the same, and that helps you with CM, helps you, and it helps you with troubleshooting and eliminating problems. You no longer have to worry about whether or not the problem was due to somebody accidentally adding a file to the file system. So how does this affect testing? Well, there's more emphasis on unit testing. You want to fail fast. Unit tests are some of the quickest way to get feedback of your code. You now have to deal with what I call the n+1 problem. It is very likely, since you're writing small discrete containers or microservices, that your service will have to work with future versions of itself. And so that when you put out a new version of your container, when you put out the next version of something, it should check to see whether or not it can work with all of its immediate dependencies at the current version and the version below. Because remember, if you're in the middle of a rolling deploy, there could be up to 2 or 3 different container versions in there, and you have to figure out how to adjust your testing framework to account for that scenario. Parallelism. You now need to place more emphasis on testing things that are happening at the same time. You have to account for the restart scenario in testing. Containers die when they have a problem and restart. So what happens? Is the data lost? Is it safe? Were you holding state in memory that you shouldn't have? Should you have been using Redis instead? You know, what do dependent services see when you die? All of these scenarios of each one of these little components failing needs to be taken into consideration. Remember, if your application was 1 component, but now it's 100 components, just by sheer statistics, you've increased the number of moving parts. One of them is more likely to fail at any time. Its dependencies need to know how to deal with that failure as well as itself. Not every combination has to be tested though. And this is true of just about anything. We don't test every combination in software anyway. We can't. It's computationally impossible. If somebody has said that they do, they're probably lying. But you do need to know what the important combinations are. Independent operation is a new test criteria. Your microservice needs to be able to at least come up and breathe life into itself on its own without anything else, even if it has a dependency on something in the database. But it must come up and start trying to get itself up and running independently. It shouldn't have to depend on any other containers existing for it to run, even if the only thing you can do is say, hey, my downstream services aren't available, here's an error message. Mocking is a must. All of your services need to be able to be mocked so you can test things without having to stand up the whole system. If you're a developer, you might not have the horsepower to stand up 100 different containers on your workstation. But it might also be a waste if you just need the 5 containers around you to do testing. You need to make sure that mocking is built into your development budget because the people writing the microservice, they're the best people to create the mock because they know what it should and shouldn't return. Integration testing will look a lot different. What we mean here is that you're going to have levels of integration testing when you're testing with other microservices, from the end-to-end scenario to the local scenarios, and those are going to get different traffic between them. You're going to focus a lot more on the local scenarios where you're just dealing with your immediate dependence. And deployments and automation, your CD must be tested. The idea is that we need to know how to add the new stuff and take away the old stuff without downtime. And the only way to do that successfully and reliably is with automation. So now you have to consider the fact that automation, your deployment, your automated deployments are now part of the things that you have to test. How does this help with Agile? As we said, manageable story sizes, manageable testing windows, etc. Manageable deployment windows. All of these things should take less time for an individual component. Automation can integrate the coding workflow with the Agile tools. Zephyr for testing, Git plus issue tracking. You can do annotations in Git so things can automatically come up in Jira or whatever issue tracking system you're using. And automated ticket creation for deploy, test, and compilation failures so that people can all react to the workflow and be consumers of the data in a responsible way instead of just having to watch the console. And this will also give you quick feedback for success and failure. So you can shift left and fail fast because all of these things are quality gates are generating this data automatically, and the correct people are being notified almost immediately. Also, it'll allow you to gain metrics for your retrospectives so that results can be measured quickly within your sprint. So we're going to take a look at an anatomy of what a microservice might look like today. Your code might be in GitLab. The first thing that might happen when you enter your CI pipeline is that you might do your static analysis, check style, PMD, find bugs. Then you might do your unit tests. Then you might do your component analysis by using dependency check to see if you have vulnerabilities. You create an immutable container, create a Helm chart to manage that container and its interaction with other containers. And then you deploy to your test environment, and then maybe you use something like Selenified to do some quick tests over the code you just deployed. And Selenified is smart enough to know only test the test cases that are relevant to the code I just deployed. Don't do a full regression. Maybe you do a full regression in a later environment nightly, but certainly don't want it in the first environment you deploy to, because that's the antithesis of failing fast. All right, moving on. Serverless. Let's talk about serverless. So from the developer perspective, woohoo, I can throw my code at the cloud and it works. And of course, everybody else is thinking, what the heck is this guy talking about? So this is literally true. With serverless programming, you create your Java program and you create your Node program and you can upload it to Amazon and bam, it starts running. And you don't need any servers. That's why they call it serverless. You don't need any build. You might need to build it if it's a Java application, but you don't need any of the packaging or any of the normal things that you have or that you're dealing with. You just put it on somebody else's infrastructure and it works. So why people will do this? Well, cost. You pay a very minimal fee per function invocation. You're not paying for any of the underlying infrastructure. You're just paying for how many times that one function is called and how much CPU time it utilizes. But you don't have to pay for a $3,000 or $70,000 server, or you don't have to pay the hourly EC2 cost for a whole server to just run this one set of functions. You just per function pay. It's more customizable than most SaaS offerings. You have Salesforce and stuff like that, but you can do much more with it. You have more control over certain aspects of your application. Business can implement IT with less staff. Developers, cloud specialists, and DevOps engineers, and there's less of a need for infrastructure engineers at this point. You're going to need a very, very savvy cloud administrator, but you're not going to need people racking and stacking servers, or you're not going to need people monitoring all of your EC2 instances anymore, because you're not going to have them. So EC2 instances are just Amazon's virtual machines in the cloud. Your potential scalability is only limited by your provider and your budget. Space, bandwidth, and compute basically is all you have to worry about and how much you're willing to pay. Your security can focus on code and architecture and leave the rest to the cloud provider. But what you do need to be very careful of is you're going to be more cognizant of logs and logging, because it's the only way you're going to be able to figure out what goes wrong. You're not going to have this external ability to tap into your application and see if it's CPU spiking or what it's logging to the operating system in syslog, because you don't have access to that anymore. It's on somebody else's computer. So what are the implications of going serverless? You're putting hardware management in the cloud provider's hands. And I'm going to say it again, you're putting platform management and hardware management into this cloud provider's hands. You're giving up the ability to do things like say, I want to use a particular version of Java. You're stuck with whatever your cloud provider has. But they also maintain it. They'll warn you well in advance when you have to upgrade. But when they tell you you have to upgrade because they're going to deprecate something, you have to upgrade. Serverless is not the absence of servers. It just narrowly defines what the end user can do on a managed server. So you're still running on a computer, just not one you have complete control over. With the change in architecture, there'll be a change in architecture and certain testing activities that you have to accommodate with serverless. We'll go, if we have time, we'll go over into that a little bit. And other testing practices don't need to change really significantly, but may need modification. So all of the changing in tests is going to be mostly focused around the low-level testing that you do in terms of integration testing and unit testing. That's going to have to look different because you don't have a literal server to run these things on anymore. But at a high level, when you're talking about behavior testing, security testing at a high level, and functional testing at a high level, that's going to look the same. CI/CD change significantly under the covers, but on the surface, it looks the same and follows the same pattern. You're not going to be deploying to a server anymore. You have to figure out how to get the code efficiently and in a CM managed way into the platform. But it's going to look pretty similar to what you have. So what's the big implication here? You need to really love and trust your cloud provider. If you have any sort of a compliance issue or security issue that you have to worry about with serverless, serverless might, on somebody else's platform, might not be for you. There are ways to do serverless yourself, which is fine if you want to follow that development philosophy. But you're still going to have to manage all of the hardware and software. And so you have to do a real analysis as to whether or not it's worth it. If you want to get the full value out of going with a serverless implementation, you're probably going to want to trust your cloud provider to let them offload a lot of the stresses of managing the application for you. So what is it like without our server? Well, there's no shell or RDP session to log into. The architecture is dictated by the cloud provider. HTML is usually put in static storage, and then you have a dynamic content and execution engine in the background. You'll usually have some sort of database, usually NoSQL database as well, to hold state. And they do things like provide Elasticache or Memcache or something also, so that you can hold state between your different components. So let's take an example. This is how the architecture would be defined, pretty little graphic, if you were to go completely serverless in Amazon. All of your static content, images, HTML would go in S3. That would be your object storage, your static object storage. Your web server would be their API gateway. That would direct your web traffic from non-static assets to where they needed to go within the Amazon infrastructure. Your execution engine is going to be Lambda. That's where the code will actually execute. Identity management is taken care of by Cognito. Database backend, your persistent content is going to probably be Dynamo. Your dynamic persistent content is probably Dynamo. Session management, either Redis or Memcached and Elasticache. And you're stuck with these offerings unless you want to do something really low level in Lambda. You're kind of stuck with what they give you. And honestly, there's a reason these services are getting bigger and bigger. It's because usually it's only what most people need. Is it for everybody? No, but typically one of these things, if only one of these things doesn't work, you stand up an EC2 instance, you put your custom solution on it, and you just skip it, but you can use the serverless infrastructure for everything else. So how do we fit CI/CD into serverless development? Well, the cloud provider must have an API to access and create the different parts of the application. The Cognito parts, the Dynamo parts, et cetera, et cetera. The CI/CD engine must have a compatible way to interface with the cloud API. If you have to do anything manually, it's not continuous, in my opinion. So you need to make sure that there's a rich SDK with your cloud provider, or a rich set of API access to be able to automate all the process of deploying code. There must be a reasonable way to simulate running on cloud infrastructure locally, at least for small parts. Deployments take time to the cloud infrastructure, and you want to fail early. If you make a stupid mistake, you want to know before you invoke the cloud API to do a deployment. Sometimes in order for the serverless infrastructure to register your change, it can take them, 45, 50 seconds, and then you start running your tests against it. But if there's something that you can do in a container locally to emulate the execution engine or to emulate the API gateway, you can find out whether or not you failed in seconds, many less seconds, before you waste your time deploying to the cloud infrastructure. And there must be a way to package the cloud configuration and the code. One of the dirty secrets of serverless programming is that you need to know how each one of those components in your cloud provider is configured when you submit your code. I don't know if I have it in here, but I have a concrete example of why that's important. But you have to keep track of every configuration element to whatever service you're using, because there's a chance that those configuration elements change between versions of code that you're using. And if you deploy the wrong version of code against the wrong configuration, it won't work. And so now this is an extra element that you need to keep track of. And your pipeline needs to take that in consideration and find a way to version those things together. Usually the answer is YAML or XML or JSON. What are some limitations of the serverless infrastructure? You got to be really careful about DDoSs. They can get expensive if you don't have limits set. Your costs will scale with the size of the attack, so you want monitoring as to how much traffic you're taking in. And it becomes a real business critical thing to look at and to know whether or not the traffic is real or whether or not someone's just trying to take you offline. But Amazon is probably big enough to handle almost any DDoS attack, and they will try to make you pay for it. So you need to be careful. You need to make sure that it's legitimate. Only a few languages and versions of that language. All right, this bullet point right here, no longer true. Amazon will allow you to install almost any runtime on their infrastructure now. It used to be the case that they limited it to Node.js, Go, Python, and a few other languages. Now they'll let you bring your own runtime. So that limitation has gone away. But you do have vendor lock-in. There's almost no moving away from Amazon once you decide to go with them. Or Azure, if you use Azure Functions and Azure databases and stuff like that. Once you're locked in, it's very difficult to migrate your code from one cloud provider to another if you've gone serverless. Just keep that in mind. Everything is public, even your test environment. You need to find ways to limit people's access, which means that, you know, if somebody gets your test credentials, they might be able to see an upcoming release if you're not careful. But, you know, Amazon's API gateway, right now, there are very little ways to limit the external entrances. They're working on it. They may have made some progress, but pretty much if you're using the serverless infrastructure at Amazon, some aspect of your infrastructure is going to be open to the public. And so you need to make sure that it's locked down. SDKs for local testing are still a little bit immature, but they have progressed greatly in the past couple of years. Things are really starting to come up. When you're doing serverless, some traditional testing methods break down. Log retrieval and log monitoring, for example. There's no more box to log into. You have to be familiar with the cloud provider's logging facilities, how often they update, and you need to make sure that your code is set up to log properly. There's no more private testing environment. It's just on the infrastructure. You just have to make sure it's gated properly with credentials. RBAC testing requires a test case for testing all access of all of Amazon now. If you give the wrong permission to a particular function or service, it could delete your account, your entire Amazon account. So RBAC testing requires thinking outside just the services that you currently have. Recognizing when there's a real functionality error and when you've just hit a memory or other resource cap. Serverless infrastructure limits each invocation, and you can adjust those limits, but the default limits are quite low. And if you have a function that's not behaving as expected, it might just be because it's taking too long to respond and your provider's infrastructure is killing it midstream. And you have to have a way to know how to see that error. It's very hard to conceptualize if you've never done it before, and it's a gotcha to people just coming over to serverless. Collecting coverage results becomes a little bit more complicated from integration testing because you no longer have a way to get to things in the cloud infrastructure. I don't know how to solve that particular problem right now, but I'm sure there's a way to do it. But it's uncharted territory. So if you rely on integration testing, coverage metrics, it's something to think about. Existing bug reports methods need to change. You need to make sure that you're collecting the cloud configuration plus the code version plus the application configuration. And security testing must be coordinated with your provider. I say AWS here, but with your provider. You know, if you try to violate their infrastructure and you don't coordinate that with them, they might shut down your entire account. Also, word of advice, if you do security testing, make sure that you do security testing in an account other than the one that hosts your production environment. Because if you accidentally violate one of their basic tenant no-nos, they will just shut down your entire account. So save yourself the heartache. So what are my testing takeaways? AWS configuration or your cloud provider configuration is as important as code. Find a way to test the configuration and make test cases that explicitly look for configuration issues, not just code issues. Ensure code artifacts have a way to clearly map to the configurations, and ensure your AWS configurations can be managed in an audible way. So that means cloud trails or something like that, so you know who's changing what and when. So here's a real world example of why that's important. I had this code, and I had the local SDK, and I was running my test cases locally, and everything was working exactly the way I was expecting it. I had a switch statement to do different things based on what HTTP method I was using, and then a default catch-all in case one of the methods, it was a method I hadn't accounted for. And when I was deploying my application to the cloud infrastructure, I was only ever getting the output from the default, even though I was doing HTTP gets against my function. And I couldn't understand what the problem was, because the code was exactly the same. I expected it locally, I inspected it on the cloud infrastructure. Everything was the same. What was going on? There's a difference between the SDK that I was using to test and the actual implementation in the cloud. In the cloud, when you deployed your code, there was a little checkbox that you had to check, use Lambda proxy integration to get all of the HTTP request types, headers, and information through the Amazon API gateway to the Lambda function. And when you were testing locally, this checkbox was automatically checked, but when you're testing in the cloud, you had to make sure that your application had that checked. It cost me days of trying to figure out what was different, since the code was the same on both sides. And it turned out the issue was a configuration issue. And so that's why I say these configurations are much more important than would normally be the case when you're deploying your application. All right, so let's get to wrap things up a little bit. Why would we do serverless? Well, a good DevOps team can easily embrace the serverless world. It's not going to be much of a change for them. Testing from a 10,000-foot level looks mostly the same. Your cloud configuration is code that should be tested in part of testing. And your identity management is important because you don't have closed off test environments that are separate from the outside world anymore. RBAC testing should be both positive and negative. Your security testing changes since you're going to be wholesale abdicating certain responsibilities to your cloud provider. Some things are just going to be their problem now. And other things like coordination with your cloud provider is going to be a new SOP you have to take into consideration. And also you may have to figure out how to wedge things in your application to get information you need. Test locally everywhere you can, even if your SDKs are immature. And understand what information needs to be in a defect report, and automate as much of that information collection as possible. So when there's a bug, you can press a button, generate a report, and you have your cloud configuration, your application configuration, and what version of the code it was against, so that you can do real troubleshooting. So as a whole, what are the benefits of microservices? Microservices, by the way, map very well to the serverless world as a serverless function. That's how you can do microservices without containers in a very real implementation. Microservices allow for fast change, testing in smaller units, and very low downtime deployments. Practical experience using microservices in a CI/CD pipeline. Kubernetes, it's basically using microservices in a CI/CD pipeline. Kubernetes is how you're going to be able to do that, and you're going to be able to take all of your microservices, get them in your pipeline going, and basically show that this is not just theory. that you can get from A to B in small bites really quickly going through your pipeline. Benefits of serverless. It can be cheap. In most cases, it will be cheap for what you want to do because you don't have to manage an entire EC2 instance or an entire application stack, just your functions and services. Serverless components allow you to create microservices-based architectures very easily that kind of enforce the small orthogonal thinking. You have to really try to make your Lambda functions not microservices. It takes a lot of effort. You can do it, but it takes a lot of effort, especially since they limit the size of the code package you can upload to their platform. And how it changes testing. You do offload some of your testing liabilities are decreased. You don't lose any of your functional liabilities, but how you're testing infrastructure, how you're testing the platform, that's all in the cloud provider's hands. So in a lot of cases, it can lessen your testing burden. And also, when we think about how we implement serverless, we need to understand why the cloud provider is important and what some of the gotchas were. I pointed one out with the differences between the SDK and the actual implementation, but also something like cores and infrastructure configuration. Cores is really something that's going to hit hard in both the serverless and the microservices world, and is built into a lot of these frameworks. If you don't know what cores is, it's cross-origin script sourcing, I think. Basically, what it allows is for one set of services to access another set of services, even though they're on different websites. And cores allows them to create some sort of a trust. And this is really important because if you didn't have that trust, somebody could, for example, build a mock Capital One site using Capital One's resources. But since Capital One uses cores, the minute they try to do that, when the request comes in from the attacker's website, Capital One's resources using cores would then deny and not serve that material. But before cores was a thing, it would be possible to have Capital One's traffic pass through another website using all of Capital One's assets except for the login and password. And then you'd be able to harvest peoples and configuration. But it's a gotcha if you haven't thought that way before, thinking that your components are going to have to take this into consideration right now when they used to be all under one website. So these are things that you have to think about. With that, I will open the floor to questions.
All right. Go ahead.
Oh, sorry. I wasn't speaking over anyone, was I?
Just Gene, don't worry.
All right. Sorry if this is a potentially awkward. Yes, never mind. So you mentioned that DDoS attacks could be very expensive, which makes sense because there's no real limit to the traffic that they can maintain because they can just keep provisioning new servers and stuff. So you mentioned like you would have to monitor that. I'm wondering if the methods for monitoring that, how to do that. I don't know if that's like an easy answer.
So most providers have that built in, but you have to be cognizant to turn it on. And have the alerts sent to the right person. If all of your alerts are going to your bill, the person who pays the bills, and they're like, what's this? What's function 32? And why hasn't it been invoked a million times? Spam. But if it gets directed to the ops people, they're going to be like, oh my God, we're being attacked, shut things down. And so you have to make sure that those alerts and pathways are set up correctly. Now, in a lot of cases, the cloud provider does give you those facilities, but you do have to configure them.
All right, that's fantastic. Thank you for answering that.
So Glenn, maybe a little bit related to that, this is Rich. Related to logging, you mentioned log aggregation and collection of logs and stuff like that. If I'm running in a Kubernetes space, I might be running, I don't know, Elasticsearch or Kibana or something like that to collect those logs and make them available. If from your experience and what you've played with in like an Amazon space, do they provide a service kind of already that harvests the log output of whatever service?
Yes.
Okay.
CloudWatch has many different facilities to do
Oh.
that. And you just need to make sure that you format your logs so that you can write meaningful reports in CloudWatch. Things need to be formatted a specific way so that you can use their internal utilities to do it.
Okay.
If you weren't happy with CloudWatch, you could actually use what they call a fire hose. It is literally called a fire hose. And you could dump all of the results to your own Elk stack or your own Kibana stack, whatever you wanted.
Okay, cool. Thanks.
Hey, Glenn, I noticed your answer to these couple questions and also to some of the potential problems you're pointing out is that using serverless and containers and microservices requires that you are, I guess, more disciplined about a lot of your practices and a lot of your testing. And you want to talk a little bit about that? I mean, I know you pointed out it was more important, but is it just the risk, or what? I guess what kind of level of maturity do you need in your development before you're going to start trying this stuff?
So at the very least, the minimum, and the minimum's not enough, but at the very least, you need a strong set of automated configuration management. And that means using technologies like Helm or GitOps or something like that, so that you have a clear idea of what it is you're deploying. Because if the minimum makeup of your application is 100 different containers, there is no manual and process in the world that's going to be able to keep up with that. You have to have some sort of tool that does it for you and does it effectively. And so you can't just compile code and throw it somewhere, which is what I've seen people do. And that's one. Two is unit testing. You need to be able to get fast feedback. When your code eventually meanders out into a static environment for widespread usage or testing, it's going to have a bigger impact if it fails in an unexpected way. And you want unit testing to cover those failure scenarios, so that if you're, at the very least, you want that automated unit testing to cover the failure scenarios so that you fail properly, right? It's not that your component can't fail. Like I said, with these fine-grained systems, just by sheer numbers, we expect more small individual failures, but you have to fail properly. You can't fail in a way that's either going to cause a cascade or choke up resources, or you can't fail in a way where you're holding some critical resource and never get it back. Or you can't be in these situations, the zombie scenario is also extraordinarily dangerous because everybody thinks you're alive, sending you data, and is just waiting, right? And so your unit testing needs to be able to flush out those scenarios so that those costly mistakes don't make it into production. And then automated quality gates and dashboarding are really important. You have to have some level of test automation. If you're going to move faster, you're going to generate more information. You need ways to funnel that information and make it useful. That's why information radiators and dashboards in your CI/CD pipeline are critical, because you're never going to be able to manage that information by hand. Gone are the days of the test QA manager with a thick binder and a whole bunch of checkboxes and screenshots. That is an hour's worth of material, where in the past that may have been generated over 3 months.
Cool.
I have a question. So I'm going to describe a hypothetical project which I'm currently working on. And when my question is, so if I give you this project, would you move it to microservices, and why? What would be the motivation? So the project is a single application, which is SPA, single page application. So the backend consists of RESTful services 100%. and it's totally stateless. It's a single web application, so all the RESTful service endpoints reuse domain logic heavily, and it's a single code base, and it's a single team consisting of 6 engineers. So the question is, would you try to split it up? Oh yeah, and we're looking to deploy in Docker, but as a monolith, right? So with the single container, well, single jar, maybe multiple containers horizontally.
So
that's kind of a current target.
I would base this decision on, so first of all, we live in the real world where we have budgets and timelines. And I would base this decision on how long I think the application is going to be around and what my budget is. And if the answer, and these two things need to be taken together. But if the application is going to be around for any length of time, a significant length of time, over 2 years, I would break it down. You're going to start seeing benefits once you can break off small pieces of functionality. You're going to see benefits in testing, reliability, return to service when there's a failure. The problem with monolithic applications is that even if they're stateless, sometimes it just takes them a while to get up and running. So I would, and if you were looking for ways to do that, there are people, I have a lot of experience helping organizations do that. And I have done it for several organizations, and they've always seen a benefit by breaking it into small pieces, as long as the application is going to be around for some length of time. If the application is going to be decommissioned in 6 months, don't bother.
Yeah, I think I would add to that as well, Glenn, that it depends a little bit on whether those pieces you're talking about can really be split. One of the mistakes I've seen people make is they take some monolith and they split it in, I don't know, half or 5 pieces kind of thing. However, what they realize is that those 2 or 5 pieces don't really work very well independently, right? They share a data store that have really closely cross-linked pieces of data or something like that. Or it becomes really hard to define what the interface and the contract of those independent pieces look like. And I use the word independent in quotes there, which is they think they're independent, but what they realize is that there's a lot of subtle behavior within the 2 applications where behavior, changes of internal state and things like that affect what the other side does. And they have a very hard time defining what that quote independent contract for that interface should look like. And then what they end up with is let's say two independent services that really aren't independent, and they have to build them and ship them in concert with each other. So you end up with 2 pieces that really always have to be deployed together because you really don't know if the new version works with the old version of the other one, kind of thing. So what you've done is split, in just a second, you've split 2 nicely compiled, tightly coupled pieces together into 2 quote-unquote independently coupled pieces that unfortunately are still really coupled, but now you have no way of really linking that coupling together through compilation and unit testing and things like that. So you're kind of stuck with this weirdly hybrid application that's really hard to manage. And that's one of the pitfalls that happens. So that's one of the things I've seen. And Glenn, I know you've run into this as well.
Yeah. So what I will say here is, Rich brings up a good point, but it's even more insidious than that. There are 2 things. One is that the institutional knowledge that created those services may have left. And this is a common scenario. So there really is no way to figure out what that contract is, because the knowledge might just not be in your organization anymore, right? And so with that, I will tell you that breaking an application up into smaller pieces to fit this paradigm, it takes effort. It has to be a concerted effort, and people have to be dedicated to reaching the end goal. The second thing I will tell you is that because the application was tested as a monolith, any side effects were also tested. And when you pull those pieces apart, all of a sudden the side effects might not be happening anymore. And so you may have side effects that nobody, not even the original designers, knew about. But the application was working because of some side effect. But now that these two components are separated, the side effect doesn't happen and you have a failure. And let me tell you, those are really hard to find. So you have to open up yourself up to the possibility that these things are going to happen. And you just have to know, you have to expect it and know how to deal with it and have a really good set of tools to get you through it. But if you're, one of the other methods that I have seen for migrating to microservices is you start by leaving all of the functionality in the old legacy blob of an application. Any new stories or requests or features are now a microservice, right? And you build on top of the legacy application in some way. It might require creating a facade, it might require doing something else. And then eventually you just start deprecating pieces of the old application as you no longer need it, as your new microservices start to pick up some of the slack independently. And eventually you just phase out the last piece of the monolith, and that takes a lot more time to do. If your organization is truly invested in Agile and DevOps, that's not such a far-flung idea, because your team and the people you're going to be working with are going to be providing consistent effort and capacity to that project. And so you have the time to work with.
But I have, so, okay, so I think I understood the sort of viewpoint. My follow-up question is, so what, all right, so let's say you make a decision to do it, what do you do with the shared code base, right? So like in this hypothetical project that I'm currently working on, there are like 50 RESTful web services, but hundreds of domain logic classes, which are all used very, very heavily reused among those, 50 RESTful endpoints. So how do you manage shared code base?
So this depends on how the code base is shared. Okay. When you say shared code base, it's a little inspecific in my experience. Are you talking about the fact that literally people have copy and pasted the same bits of code over different parts of your source code repository? Or are you talking about everybody's using the same jar file or the same?
Yeah, it's a single application, right? It's a single application. So yeah, even though there are, 50 RESTful endpoints, there is a whole layer of domain logic, which is reused very heavily among them.
Well, if you have RESTful endpoints, I mean, you can start by turning on endpoint versioning, and then each endpoint can start to become its own microservice.
No, I understand that. Well, part of it I'm having trouble with, I have like 100 domain logic classes, which are reused. So what do I do? Do I separate them out into separate repo? How do I split them up?
Unfortunately, there's no, I'm sorry, but there's no one answer to that question. It's something where I would have to review the application. The reason being, one of the tools that I would use to do that, right, is a data flow analysis. I would try to figure out what the inputs and outputs are and how they flow through the shared code base to figure out good points where I could draw the lines. And I would use a data flow analysis to do that. Maybe perturb it with some random data generation or something like that. And take a look at the coverage as each input is perturbed, as each output is perturbed, and see if there were bits that I could break off, right? And that's just where I would start. After that, if that didn't yield any results, because it might not, I would do an in-depth code review and architectural review, but I would do it without any prior knowledge. I would do an independent review of the code base and take a look at what I thought was going on, maybe poke and prod at the application a little bit and do some experimentation. and again, try to find those bits of functionality where one of two things would happen. You would find pieces that you could A, cleanly break off, usually, and then B, you would create a roadmap so that you could change the core logic of the application so that it would, in the future, be amenable to being broken up. Some things you just need to refactor in preparation for breaking the application up into smaller bites. And it would be a conscious choice to potentially touch code that hasn't been touched in 10 years, depending on how old the application is. I mean, those are the various methods I would approach it.
Yeah, I have a couple thoughts on that as well, if I may, which is when you're splitting code like that and you have things like shared code, whether that be, you know, a library of utilities like your logging framework or something like that, or whether it even be like a business logic basis, right? I think Glenn absolutely hit it with, if you can separate, I mean, there's the purest sense of microservices where you never want to share code between anything. If you ever want to have something that's a shared piece of code, you make it into its own service and you invoke it somewhere, right? So for example, even your logging framework that might have been a shared jar at some point as a utility, you would no longer share that jar between two different working pieces of your service, but rather you would turn the jar into a service in itself and you would just interface with it a different way. The implication of that, though, could be that instead of, you know, a directly compiled function call to invoke your logging, now you're making a REST request across a network somewhere. So there's performance impacts of that. It does mean that in those kind of cases, you know, people make exceptions, right? They still publish utility jars and they link them into multiple parts of their services, right? So that's one particular thing, and I don't know if you run into that. The other one that I think you indicated, Dimitri, was, you know, I have a business logic set of shared code kind of thing. That actually might lend itself very well, again, to something that truly is a remote service, which is that shared code really becomes one of those things that you separate off into your microservice. And I don't know if that applies in your situation. And that's why what Glenn said is absolutely appropriate, which is without sitting down and really investigating what the architecture of your app is, it's hard to say what that answer is. And I don't know what your situation is.
But isn't it true that for many cases, I mean, to exaggerate it to an absurd extreme, if you're sharing printf in all of your microservices, you wouldn't make that a microservice, right? So it would be a library.
Yes. This is exactly kind of where I'm struggling, right? So there's just bunch of classes which are shared, utilities and what have you, and some domain logic stuff and things calling storage procedures, right? And we're all share, we're all called from RESTful endpoint. So what do I do, right?
Yeah, and there's, I mean, I got into a battle on this on my last project where there were some people who were like, well, it's a microservice, you're not supposed to share libraries between it, so if you need a printf function, just re-implement it yourself, right? But let's be honest.
This is sorry for interrupting, but
yeah, no, go ahead.
Very, very important point. I think for me, so I sort of in my opinion currently, and again, I did not really use microservices in production. But I'm of opinion that it's a technical implementation of Conway law, right? So the great motivation is when the system is large enough that it cannot be managed by one team, right? So you have at least two teams which are developing different parts of the system, and that. So now nobody wants to share, or nobody. Not in my backyard kind of code. Why would you manage that? So, and when you start breaking out left and right, so one team is deploying on its own schedule, where microservices, another team deploying where microservices. But this I can see definitely. But in one team, with 6 engineers, what would be what would I get? I get a lot of complexity, but I'm already, stateless, and I'm already been deploying in Docker, and I already will scale horizontal. Why would I split?
Well, I'll give you a couple of reasons. One is that bug resolution will become faster because you're dealing with small discrete units. You worry less about side effect. Side effect does happen, but it happens in a particular way. Basically, if you start breaking down the application, you can focus testing more. Your testing can be more refined, and in the end, you'll be able to use your automated tests to be a better predictor of the user experience, because you'll be able to just focus. You'll have ways to focus on just the things that change and just the functionality that changes. So that's one. Two is, do you require any downtime to deploy right now?
No, this it's not. So this is sort of re-architecture. We're not in production yet, but we're currently working on it. But when we'll deploy into Docker containers, several of them. So we envision zero downtime.
Docker containers by themselves don't grant you zero downtime. What grants you the zero downtime is the fact that you have multiple copies of things running. And that is easier to test for. Okay, so remember the testing scenarios I was talking about? When you have a small discrete unit and you now have to have 3 of them up and you have to make sure that they're interacting in various states, the number of inputs and outputs that you need to be concerned about with these small discrete units is much smaller. And that's what's going to give you your zero downtime deploys, not Docker. Docker is just a way to isolate programs in an operating system.
No, yeah, I understand that. I'm just saying that we'll have not one container in production, right? We have 5, right? We can bring them down one by one and redeploy,
right,
with rolling deployment.
But the bigger the application, the more states you're going to transition as you bring one of those containers down. The heavier the testing burden and the more that can go wrong, as opposed to if they're smaller. So if you're talking about what you're buying, you're going to buy a smaller test surface area for keeping your zero downtime deployment. What you're going to find is if you put your large shared code base into Docker containers, it's very possible that you might not be able to predict all the scenarios and states that the application as a whole passes through as that container comes down. And you might find that just cycling through containers and bringing them up might not be enough. The more that's in the container, the more that you have to account for. I mean, I understand, especially with a code base you're familiar with and that's been tested and people are fairly familiar with its behavior, what the hesitancy to open the hornet's nest is. That's why I said it's an economic decision too. You have to decide how much resources you have available to dedicate to this. But the cost-benefit analysis, the longer the application is going to exist, the more benefit there is to doing it and starting down that road. So that's it.
There's one thing, I don't know if it's been mentioned, but also the communication between microservice is several orders of magnitude slower than a function call, right?
It depends. So if you're going to that's why we focus on the lightweight protocols. There are protocols that you can use that are not as fast as a function call. And when we say function call, I'm assuming you mean like like you're in C or C++ or something like that, and you're calling a function from the main thread, right?
Right.
It's not quite as fast as that, but you can get communication protocols that are close. And then you go up a little bit to like LDAP, which, yeah, is probably an order of magnitude more expensive, but not bad.
Well, I think the flip of that's important too, that you can just because you split it into microservices and you get the lightweight protocols and everything, you still have to remember not to do stupid stuff with your network, like route everything through a server that's on a different system so that everyone can snoop on it and all that. Not that you have any idea what I'm talking about, Glenn, but it is possible to build really bad networks where everything loops through a single firewall for millions of users, stuff like that, right? We've worked on a couple networks that were just made. You'd think they were designed to make microservices an impossibility.
Hypothetically, route all your traffic through, say, Georgia.
Yes,
So-
something like that.
So we had one client, and I worked on this client with Gene, where they literally had to buy the biggest piece of equipment Cisco had to offer because of this. And they were one of the only consumers. It was wild.
Yeah, there's another one of our clients that does just, we're not doing microservices or anything like that, but every request that you have in the cloud, they have not moved over their Active Directory, or they originally hadn't moved over their Active Directory into the cloud. They still had that in an on-prem data center, but now they do all their monitoring and DNS resolution and URL routing, and they do SSL termination, meaning basically they launch a man in the middle on their own site. But everything goes through an on-premises box, even though it starts in the cloud. So I'm going from one cloud box to a cloud box next to it, and that has to get routed out of the cloud to their on-prem service, get the response, go back. The response goes back. It's like 4 round trips for every touch point, and it's just, you know, again, makes it impossible to do this. So you can definitely build up network complexity to make it unsuccessful.
Yeah, one thing I will say is that moving to microservices does take a concerted effort. You will lose time refactoring the application instead of adding new functionality. And so whoever cuts the check has to be on board with the cost-benefit analysis of that. And unfortunately, a lot of business units are not good at predicting the future value of even paying down simple technical debt. So something like changing architecture to microservices, you really need buy-in and support for. Otherwise, people will say, well, you tried it and it failed. Well, no, it's a process. It's not instantaneous results if you want the same level of quality. So you got to, if you're transitioning an old monolithic application, you have to factor in the time. It's going to take time to do it correctly. And if you don't have the time, there are extreme measures you can take, but this is not an overnight thing if you're going from the old way to doing it to the new way of doing it.
I think Keith's point is very valid, that as you split these things up, you need to take into account the cost of invocation. You know, it's no longer a function call. So, you know, kind of that pathological example we said earlier with like printf. Like making printf into a REST call would be the worst decision ever, right? But, you know, it's just all these factors. It's not simple. And I gotta be honest, I've seen people screw up microservices more often than I've seen them get them right. Right? And it's a learning effort, right? And it's splitting up into federated services and going in the right direction, and then realizing that what really drives what you're trying to accomplish is rate of change and granularity, right? When you, and kind of, I think to Dimitri's point, like if what you're doing right now works for you, there's very little compulsion to change. Like, oh, well, we're deploying this thing and we're building containers and we're deploying it and it's working. If it's working for you, then okay, maybe that's not the right place that you need to institute change. Maybe there's other places. On the other hand, if what you're finding is like, oh my God, we have this behemoth and you know, it takes I need to make one little change to some piece of my system, but I have to rebuild and regression test this entire insane thing. That's where you start looking at not splitting your application in half, but rather taking this one little tiny piece and pulling that thing off and putting it in its own repository with its own build system and its own deployment mechanism, and figuring out, you know, how do I what does it look like changing this one little tiny thing versus changing this big behemoth? And when you figure out that that little one tiny thing, like it's easier to test, it's easier to deploy, it's easier to update, it's easier to understand, then you're in the right direction, right? Then you take that second piece and you slice that one off, and suddenly, you know, it's going to be a while, but maybe finally your Amazon and the web page system or the consumer system they have is 452 microservices assembled on a single page, right? You're not going to get there tomorrow, but take one little, don't split it in half. Take one little piece and start with that and see where it goes. It was a good talk, Glenn. Lots of good questions.
Thank you.
Yeah. All right. Well, if that's it, I did send out the announcement for our next talk with Ryan and Derek, and that's going to be on Wednesday, June 24th. I set it to start at 6:45, and we'll get the talk started at 7 and 7:30. If you have any ideas for talks, if you have a talk you would be willing to share, please contact me on the meetups group and let me know. And like I said, I'm going to try to get this onto a monthly cadence. So thank you all for coming. If there's nothing else, have a good night.
Thanks, Gene.
Thanks, everyone.
Yep. Thanks, Gene. Good talk, Glenn.
Thanks a lot,
Thanks,
Glenn.
Ryan.
Yeah, thank you, Glenn. Very interesting.
Thanks, Glenn. Very thorough. Thank you.
Thank you. Very excellent talk.